Good morning, folks. How are you? I hope you had slept well. So thank you very much for being here this morning. We will continue with the basics of logic design. Today, I think it's a very interesting lecture in which we will see how actually an arithmetic logic unit is implemented with hardware. As always, remember that part of the material in these slides is taken from the book. So basically today we will see how a 1-bit arithmetic logic unit is implemented in hardware with the hardware components we have seen, we saw yesterday, the gates and or multiplexers and so on. Okay. Before starting, I would like to mention yesterday someone asked me what happened with the selector with multiplexers. Someone asked me if this selector here can be of more than 1 bit. So the answer is that selectors only have 1 bit. So if I have multiple inputs, I will need more selectors. For instance, as I have mentioned, selector is only a single bit, so it's only 1 or 0. So we have, if I have n data inputs, how many selectors do I need? So there is a very complicated formula here. I don't want you I just want to show you this. You don't need to know this, but just for having it clear. So if I have 1 input in the multiplexer, I only need 1 selector. If I have 2 inputs, I only need 1 selector. Okay. In the multiplexers we saw yesterday, for instance, if we have 2 inputs, A and B, we only need 1 bit to select that input. With 1 bit, we can select those 2 inputs. But if we have more data inputs in the multiplexer, let's say I have 4 data inputs, then I will need 2 selectors. Okay. If I have, for instance, 64 data inputs in my multiplexer, then I will need 6 selectors, and this is obtained. This number is obtained with this formula here, with this equation. Okay, so basically, if I here 2 inputs, I only need 1 selector. If I have here 4 inputs, I need here 2 selectors. Okay, and if I have 64, we have said that we need 6 selectors here. Okay, then. So I hope that is clear. I have added those slides at the end of yesterday lecture slides, so you can find them on Canvas. Okay, then. If it's not clear, just let me know. So let's continue then with today's lecture. As I has mentioned, we are going to see how a basic 1-bit arithmetic logic unit is implemented in hardware. So if you remember, we showed time ago that the components of a computer are the ones we have in the screen. So we mentioned that we have memory, we have also the processor, and the processor was composed of the control unit and the data path, and we show that the data path internally has registers and the arithmetic logic unit. So we more or less know what is happening in all these components. So I have my program. When my program is executed, it's loaded into memory, and as we have seen in the labs, we know how instructions and data is placed in the memory. So instructions and data are placed both in the memory. Remember the store concept program. Then instructions are executed one by one, and those instructions are executed in the arithmetical logic unit. Okay, so instructions and data are in the memory. The control fetch one instruction and tells the data path to do that instruction, and so on. So here we are going to focus today in the hardware, which is inside this arithmetic logic unit. So for representing this arithmetic logic unit, we usually use the symbol that we have in the screen. And for instance, here, a 1-bit arithmetic logic unit means that we have 2 inputs, and then we have 1 output as a result. And inside this, we can have, as we have mentioned in the past, the arithmetic logic unit is responsible of doing operations such as and, or, addition, subtraction, and so on. Okay. So today what we are going to see is how actually this arithmetic logic unit is implemented in hardware. And for that we are going to use the components we saw yesterday, and OR gates, inverters, and multiplexers. Okay. So let's start then. So here, for instance, we have an arithmetic logic unit which only performs AND and OR. So here we have an AND gate, here we have an OR gate, and this multiplexer is going to select, okay, I want to do the AND. In that case, I will follow this path here, or I want to do the OR. In that page, I will follow this path here. And that will be selected by the input selector of the multiplexer, which will be 0 for an AND and 1 for an OR. And with this, we will have the hardware, which is inside a 1-bit arithmetic logic unit for implementing an AND and an OR gate, and an OR logical operation. Okay, make sense? So now, let's see how do we perform addition, for instance. For now, we will assume that this is like a black box which just performs the addition, and we will see later which is actually happening here inside this black box. Okay, so here we have what we call 1-bit adder, which just has 3 inputs and 2 outputs. So the 2 input operands are A and B. Then we have a single output, which is the sum of A and B. And then we have an additional output, which is the carry out. Remember that, for instance, if I add 1 plus 1, the output will be 0, but the carry out will be 1. And then we have also a carry in case this operation is done after a previous addition. Okay, so this is what we have seen when we saw the binary addition with 2 inputs, but here we are considering also the carry in and the carry out. Okay then, so we usually refer to this as a full adder or a 3-2 adder because it has 3 inputs and 2 outputs. Remember, the inputs are A, B, and carry in, and the outputs are the sum and the carry out. There is also a version which is called half adder or a 2-2 adder, in which we don't have the carry in, we only have the carry out. This could be, for instance, when I'm implementing an arithmetic logic unit of more than 1 bit, perhaps the first bit doesn't need a carry in. Okay, as well. Okay, so now let's focus on the full adder, on the 3-2 adder. So what will be the truth table for this 1-bit adder? So we have seen how to do these truth tables. Now imagine that the inputs we have here, A, B, and carry in, and the outputs will be carry out and sum. So what will be the truth table for these elements? Okay, so I have, as yesterday, we have on Canvas, we have a quiz here. Okay, so yeah, if you can do it. I give you some time. You have distractions also on this Canvas page, and I want you to complete this truth table for this exercise you have in Canvas. Okay, the time is over. I hope, let me check if I got some responses. Okay, so we have some responses here. It seems that most of you, 86%, answer it correctly. So let's see what is the answer for this exercise. Okay, so what we are doing here is adding A plus B. So 0 plus 0 is 0, and the carry out is 0. 0 plus 0 is 0, and if the carry in was 1, in this case, the sum is 1. Okay, this carry in can be from a previous addition. Then we have if 0 plus 1 is 1 and the carry out is 0, 0 plus 1 and with carry in 1 will be 0 and carry out 1. It will be the same as doing 1 plus 1. Then we have 1 plus 0 with carry in 0, the sum is 1 and the carry out is 0. Then we have 1 plus 0 with carry in 1, the sum will be 0 and the carry out will be 1. This is what we have seen in binary addition, but here we are just putting it in a truth table. Okay, you have also here in the comments what I mentioned with words. And if we continue, 1 plus 1 with carry in 0 will be carry out 1 and sum 0, and 1 plus 1 with carry in 1 will be sum 1 and carry out 1. Okay, I think this is simple. So can you tell me now what is the logic equation for this carry out, so for this truth table? So what will be this the logic function for this? For that, I have a form for you. So I'm going to publish in the Q&A. So it's published now. And yeah, I give you some time to try to see what is the logic equation for this carry out. Okay, the time is over. So someone is asking why are we adding the carry in to the sum? So remember, if you remember in the binary addition when we were doing the binary addition by hand, you remember that if we add one number and then for calculating the addition of so if we were adding one bit, if we then go for the next bit for the addition, the carry out of the first addition was included in the sum of the next bit. So here we are doing exactly that. In the end, we will see how this hardware is connected, and probably you will understand better why this carry in is an input of the sum. But if you remember what we were doing in binary addition, that we do this the binary addition by hand, then the carry out of one addition was was put as an input for the next addition. Okay, then, so let's see how we have the logic equation for carry out. Someone has also told me if we have done this previously. So this is just a truth table, and logic equations, we have also seen how to convert truth tables to logic equations. Remember, we have seen truth tables, Boolean algebra, and also Carnot maps during this week, okay? So let's see for doing now the logical equation. So you can do as we have done in previous lectures for calculating this logic equation with this truth table, but now I'm going to show you a method which maybe is more simple. So for instance, from this truth table, let's see when the carry out is 1. Why the carry out? Because it's one of the outputs. We have two outputs, the carry out and the sum. So when the carry out is 1, so one is carry out is 1 here and here. So values of the inputs when carry out is 1. We can summarize this in this table. Okay, so the only thing I'm doing here is I'm selecting only the values I'm interested in, the ones which are 1. And then I'm just reducing the table with the values in which I'm interested in. Okay? And the carry out then is 1 when I have these inputs. So then it's easier for me doing the logic equation for carry out. So the carry out will be 1 when B and carry in are 1, which is this red, what I have highlighted in red. The carry out will be also in this case 1, okay, regardless of A. So if B and carry in are 1, regardless of A, if it is 0 or 1, it doesn't matter, it will be 1. Then we have also that the carry out will be 1 if A is 1 and carry in is 1, which is highlighted here in blue. And finally, if both A and B are 1, then I have also that the carry out is 1. Okay, so this will be the equation for the carry out. Okay, so all we have done is just from this truth table selecting the values in which the carry out is 1. I discard the ones in which is 0. Then I select the input values for when carry out is 1, and I build this logic equation. So now I'm going to do something similar, but in this case, what we want is we have the truth table, we have the logic equation. So what will be the implementation of this with gates? You remember here yesterday we showed the AND the OR gate. So for this I don't have a form, but yeah, I give you some time. Okay. Okay, thank you so much. The time is over. So let's check. What is the answer here? So here, what we have done is something similar to what we did yesterday. Okay, so sorry, something has happened with the Q&A. I hope you are still listening me because I don't see any new question. Okay, if you can hear me, please thumbs up because I don't know if the Teams is working well. Okay, thank you. Okay, so let's see. So how do we implement this carryout with gauge? So for instance, let's focus on the first component of this equation. So we have this, we have that the carryout will be 1 is if B and carry in. So if both of those are 1. So this is implemented in this AND gate. So we have the carry input here and the B here. Remember that these black dots are like bifurcations. We don't have to confuse those with the bubbles which are for the inverter. So this means that the carry in goes here and here. So it's an extension of the signal. Okay. So then here we have carry in and B, and here we are doing an AND. And this is actually this part of the equation. Okay, so the next part, A and carry in. Similarly, here we have the carry in and the input A, and it's done in this AND gate. And then we have here again another AND gate, which is B and A. And then we have an OR gate for all those three outputs of the AND gate, and this is actually the output for the carryout of or other. Okay. So then we have done this with the carryout. So can we do this the same with the sum? So what will be the logical equation for the sum? Now we have done the carryout. Apologize, some people is saying that you don't know how to do the carryout. I thought that as in previous lectures we have seen truth tables, you were now familiar with that. Apologize if that was not the case. So hopefully now that we have seen also how to do this for the carryout, you can do that the same for the sum. So now I want the logic equation for the sum. Okay, for the sum. Again, now I'm going to add a form in the Q&A, and I'm going to give you some time to do that. Okay, then, so the time is over. Let me check if now we have more responses. Okay, so in this case, most of you got the right answer, but there are still some people which doesn't have the right one. So let's see. So we are going to do exactly what we have done with the carry out, but here we are going to do this with the sum. So again, when is sum equal 1? So we go to the truth table, we select when the sum is equal to 1, and then we simplify this table with only the inputs in which the sum is 1. So this happens in the rows you can see in the screen. So, and this only happens when exactly one input is 1 or when all the 3 inputs are 1. So the logical equation for the sum will be as follows. So with this part of the equation, we are saying, okay, if A is 1 and B is 0 and carry in is 0, then the sum will be 1. If A is 0, B is 1 and carry in is 0, then the sum will be 1. If A is 0, B is 0 and carry in is 1, then the sum will be 1. Okay, with those 3 components, we are saying that sum is 1 when exactly one input is 1. And then we need the reminder. So when all the 3 inputs are 1. So when A is 1 and B is 1 and carry in is 1. Okay? So now, if we want to represent this with gates, could you do something similar as we have done with the carry out? I'm going to give you also some time to do this circuit, similar to the carry out, but now the equation changes. Okay, time is over. So let's see how do we convert this equation with into a circuit. How do we implement? So here it's a bit it's similar to the one we have done before, but we have more gates. So the first part of the equation, A and not B and not carry in. So it's done in this AND gate. Someone is asking if instead of having this black dot here in order to represent that the carry in is expanded to this line and this line. So if we can just have, in this case, 4 carry-ins. So one carry-in signal here, another carry-in signal here, and another carry-in signal here. So that will mean that we have 3 carry-in signals, which is actually not happening. What is happening in the hardware is that we have only one signal and internally it's expanded. Another another classmate is also asking if we need this black dot. Yes, because here, for instance, you see the signals are crossing, but we don't have a dot. So then we know that this is just those cables are not touching one each other. Okay, so we know that this is signal A and this is signal carry in. But here we know that this is signal carry in, and as we have this black dot, we know that this is also signal carry in. Okay, so we need to add these black dots in order to differentiate that behavior. Okay, so then, as I was mentioning, this part of the equation is happening here in this AND OR. So we have the carry in negated, we have the A, the signal A, and we also have the B from here negated also. Remember, the bubbles are used to represent inverters, the NOT gates. Okay, then we will do similarly for the second part of the equation, which is here, and again we have the carry in here negated, the input A negated, and the input B without negating it, the input B itself. And we will do similarly for the carry in and for the other part of the equation. And finally, we will just sum everything here and we will get the sum. Okay, so now we know how do we get the sum and how do we get the carry out. So we actually know how to build a 1-bit arithmetic logic unit which performs an AND operation and OR operation, and we have just seen what is happening here in this box to do the addition. And how do we select in this arithmetic logic unit if we want to do an AND, an OR, or an addition? So for that, we are using a multiplexor. Notice that here I'm using decimal values to refer to the selector, to the operation. Internally, you know that this will be binary, and then for having three data inputs, I will need 2 selectors. But here, for simplifying the circuit, we usually use for multiplexor decimal values here to do the circuit simple. Okay, so if the operation is if the operation is 0, then I will do an AND of A and B. If the operation is 1, then I will do an OR of A and B. And finally, if in the multiplexor the selector says 2, then we will do the addition of A and B, and here we will use the carry in, and also it will generate a carry out apart from the result. Okay, so let's see how do we implement now a 64-bit arithmetic logic unit. So what we are doing is just connecting the 64 1-bit arithmetic logic units, and now it makes more sense the carry in and the carry out. So imagine that here we are adding first the first bit A plus B, and this will generate a result and also a carry in, and this carry in is actually what is added to the next bit of addition. This is like when we were doing binary addition, that we first add 1 bit, then we add the next bit, and if there was a carry out from the first bit, we need to put this carry out in the sum of the next bit. So here we are doing exactly that. If there is a carry out from the previous addition, we just add this to the next one. Okay, makes sense? And here for the multiplexor, we just expand the operation in order to do the same operation in the same 64 1-bit arithmetic logic units. Okay. So this organization is usually called ripple carry, and now you know what is actually, how do we actually do a 64-bit arithmetic logic unit which can perform an or an addition. Okay, but what about subtraction? So can this hardware we have implemented do subtraction? If you remember, subtraction we have seen that is the same as adding the negative value of one of the operands. And we showed that this was accomplished by doing the choose complement of the operand that we want to negate, which was actually inverting each bit of the operand and then adding one. So this is shown here. So now we are adding also a couple of multiplexors, one here and one here. Why? Because imagine that we want to do minus a plus b. So in this case, this is equivalent to adding the negated value of a plus 1. Okay, so we have here a, and if we want to do the inversion in this multiplexor, we will select 1. And with this 1, this will mean that we are negating a. But if we want to negate a, apart from inverting its bits, we also need to add 1. What are we using to add 1 to this value? So then we are using this carry in the initial addition to add this 1. And with this, we will negate this value and have its choose complement. So if a invert is 1 and carry in is 1, it will mean that we are negating the a, and that means that we can do a subtraction of minus a plus b. Okay, so we have added this multiplexor, which allows us to invert the signal a or not, and the same will happen with b. So it's similar. With b, we will have another multiplexor in order to say, okay, invert the value or not, and if we invert the value and have carry in 1, then we will have a minus b. Make sense? Okay, so today we have seen how actually is implemented a basic arithmetic logic unit with the gauge we have seen in the previous lecture. So now we know what happens since I do my program, how it is converted into assembly instructions, how those assembly instructions are encoded into zeros and one, and how internally those instructions are executed in hardware by an arithmetic logic unit. Okay, so we have like an overall view, a basic overall view of what is happening since I write my program in a high-level language until it is actually executed. In the next lecture, we will see sequential logic. So remember that until now we have only seen combinational logic blocks. Combinational logic blocks, we don't have memory, so the output depends only on the input. Sequential logic blocks, we have memory, so that means that the outputs will depend on the inputs and also on some values stored from previous calculations. So we have some time for some questions here. Let me check if I can see any question. Someone is saying if I could repeat the last slide. So I guess is for this. So here what we are intending is to say, okay, with this hardware, without the blue things, without the A invert and B invert, we have seen that we can do A plus B. but what if I want to do also a subtraction? So if I want to do, let's say, b minus a, we have seen that for doing that, all I need to do is negating a. And for, all we need to do is calculating the choose complement of a. And that choose complement is equal to invert all the bits of a and add 1. So what we are doing here, if we want to calculate this minus a, we say, okay, we have a multiplexer, and say, okay, invert the value of a. So here we will have the value of a inverted. But apart from that, if we were adding this to b, it will not be correct, because in order to calculate the choose complement, apart from inverting a, we need to add 1. So what we are doing is adding this 1 with the carry in. So then if the a invert is 1 and the carry in is 1, we are calculating the choose complement of a. And if we add to the choose complement of a b, is the same as subtracting a from b. Make sense? Similarly, we have the same with b. If I want to subtract b from a, what I do is here b, I negate b. In order to negate or to invert b, I have added here a multiplexer, and if this multiplexer has the selector input to 1, it will invert b. And in addition, to calculate the choose complement of b, I need to add a 1 in the carry in. So if the carry in is 1 and b is inverted, then if I add, in this result here, I will have I minus b. Okay, I hope it's clear now. Someone is asking if in the exam we will need to to implement a very complex logic circuit. So I have mentioned it, but you will have like a practice exam, and you will see what you could expect in the final exam. So this week I will publish the first practice exam for the first part of the module, and once you finish the labs for the second part and for the third part, I will publish practice exam. And in the end, you will have a complete practice exam in which you will know what I expect from you in the final exam. Okay, so you will have in this week and the next one, you will have more information on this. Someone is also asking, what is A invert? As I have mentioned, A invert is the control signal for this multiplexer. And if A invert is 0, then we are not going to invert A. It's just the signal A will be the output from this multiplexer. And if A invert is 1, it will invert A. So it will apply this inverter, and the output of this multiplexer will be A inverted. Okay. Someone is asking, why do we need in here in a 3 input multiplexer? Why do we need 2 selectors? So imagine that in binary this is 0 0, 0 1, and 1 0. So we need, with 1 bit, we can only go for 0 or for 1, but there is no way with 1 bit of representing the third value. That's why we need, that's why we need to, this operation here in reality is a 2 selector with 2 bits. And with 2 bits, we can do 0 0 for the first option, 0 1 for the second option, and 1 0 for the third option. And even we could have, with those 2 selectors, we could have a fourth option with the 1 1 input selectors. Okay, someone is saying this dash above means not, the plus means and, and the dot, as we have seen in previous formulas, is the plus means or and the dot means and. Yeah, that's what they mean. So this dash here on the top is converted into an inverter or a bubble. The dot is converted into an AND gate, and the logical OR is converted into an OR gate. Okay. Yeah. Okay. So many thanks for your time. Many thanks for listening. I hope you have enjoyed it. If something is not clear, just let me know. And yeah, I have tried to do my best. So see you next week. Remember that today at 1 you will have the lab for this week. As usually on Friday at 1 we will publish the solutions with a video. And as I have mentioned, I will also be publishing starting this week practice exams showing you what I expect from you in the final exam. Okay, so thank you very much, and many feedback you could like to give me. I'm always happy to improve my lecture. So yeah, you will be more than welcome. Have a nice day, rest of the day, and yeah, see you. Bye bye. Thank you.